Life appeared on our planet more than 3.5 billion years ago. During its history, Earth underwent periods where ice reached the equator, as well as sweltering times with ice-free poles. Jungles from these geological epochs have become the home of reindeer today. Sea levels once rose 200 meters above the current level, turning continents into archipelagos, then dropped 100 meters below the current level, creating now submerged land areas. Continents moved closer and then drifted apart. Animals from 600 million years ago seem like they're from a science fiction movie, though dinosaurs are often considered the main stars of the Mesozoic Era. It's easy to forget that 400 million years before dinosaurs, a plethora of animals preceded them. Their world changed due to climate change, lack of food, or new predators, leading most species to fail to adapt and go extinct. However, they left their marks on Earth through fossils, providing a detailed picture of life before dinosaurs. Dear traveler, good morning. Today, we embark on a journey to the heart of the Proterozoic and Paleozoic eras, more than 400 million years before the reign of dinosaurs, to discover astonishing and thrilling animals. This journey will reveal our planet devastated by the worst extinction episodes it has known. But before setting off on another incredible adventure, don't forget to like the video and subscribe to the channel so you won't miss a thing. Thank you all and have a great trip. Let's travel back in time, long before the age of dinosaurs, when Earth was a huge snowball completely frozen, covered in glaciers from the poles to the tropics. Volcanic eruptions produced CO2 in large amounts, creating a greenhouse effect that warmed the planet, melting the ice and allowing different land masses to join and form a supercontinent called Rodinia, surrounded by a single ocean named Merovia. Scientists use the appearance and disappearance of animals to divide the historical periods of Earth's evolution, which are further divided into epochs, together constituting 4 epochs spanning the last 635 million years. Our journey begins in the Ediacaran period, between 635 and 542 million years ago, marking the end of the late Proterozoic era and the beginning of aquatic fauna's history at the bottom of Merovia. Bacteria and microbes brought by rain started to thrive. In 1946, Australian geologist Rex Prck was having lunch in the Ediacara Hills in Australia when he suddenly observed strange, jellyfish-shaped imprints on rocks that were 600 million years old, making one of the most important fossil discoveries of all time. Dickinsonia. Scientists believe that the oldest animal that lived in the sea was found in Australia and Russia about 560 million years ago. Dickinsonia, an oval soft-bodied animal covered in grooves formed by its body sections, could grow up to 1.4 meters in length, but was as thin as a sheet of rolling paper. It was unclear whether it was an animal, a plant, or a fungus until 2018 when a team of paleontologists detected specific fat molecules of multicellular animals in Australian fossils. However, this discovery wasn't enough to confirm Dickinsonia's placement in the animal kingdom. It could also be related to jellyfish, sea anemones, or even be a giant flattened worm. In 1957, 3 English schoolchildren found a leaf-shaped fossil in a forest in Leicestershire and took it to a local university geologist named Charnia. It seemed like a fern, but the discovery of other Charnia fossils and rocks that were once submerged indicates it was not a member of the plant kingdom. This animal lived in deep waters where the lack of light didn't allow for plant development. Since its discovery, other specimens have been recovered in rocks from Canada, Russia, and Australia. Charnia had no skeleton or shell, and its body was soft. Most fossils measure about 20 centimeters, but a related species, Charnia wardi, known in Canada, could reach up to 2 meters in length. It's assumed to anchor to the sea floor with a disc or spike and grew like a leaf on its stem. Since it had no mouth or gut, it likely fed by filtering or absorbing nutrients from the water, similar to its modern relatives, the crinoids. Another fossil from the Ediacaran period, also from the Ediacara Hills, is Kimberella. This animal was up to 15 centimeters long, 5 centimeters wide, and 4 centimeters high, with a single wide and muscular foot for movement. It used a soft but robust shell to retract its soft body in case of threat. In some rocks, the traces of Kimberella's passage suggest dentition, possibly making it the ancestor of the snail. Kimberella has all the characteristics we find in this animal today, and it can be clearly stated that Kimberella is the oldest known mollusk. Still in the Ediacara Hills, paleontologists discovered other fossils, including Tribrachidium. This animal lived in shallow waters, and with a diameter of 5 centimeters, it buried itself in the sea floor, leaving just a few millimeters of its semi-spherical body above. 3 grooves extended from the center and curved toward the edges, like the Breton Triskel. These created vortices that channeled water towards 3 pits at the top of the animal, possibly to filter feed. Researchers believe Tribrachidium's closest modern relatives could be anemones or starfish. The first animal with a shell, Cloudina, appeared to be widespread, with fossils found in limestone rocks across Africa, Asia, North and South America, Europe, and Antarctica. Its shell consisted of a stack of open cones, forming a tube corresponding to its habitat. The largest specimens measure 15 centimeters in length and 6 millimeters in width. How Cloudina fed and its lifestyle, whether it stayed on the sea floor or could bury itself, remain mysteries. However, the way these marine animals fed probably clarified their oxygen content, favoring the emergence of more mobile and energetic animals, as well as the development of their eyes. Holes drilled in some Cloudina shells suggest attempts at predation from one animal to another, setting the stage for the great predator-prey confrontations of the Paleozoic Era. At the end of the Proterozoic Era, Rodinia, the supercontinent of the time, broke apart into several continents. First, around 560 million years ago, 3 continents separated: Laurentia, Siberia, and the immense Gondwanaland. Laurentia includes present-day North America, excluding New England and Newfoundland but with Northern Ireland and Scotland. Siberia corresponds to current Russia, and Gondwanaland includes Africa, South America, Antarctica, India, China, Southeast Asia, Australia, and Southern Europe. 520 million years ago, a new continent called Baltica broke away from Rodinia, resembling Northern Europe. Gradually, the opening of a new ocean, Iapetus, separated Laurentia from Baltica and Gondwanaland, marking the beginning of the Cambrian period, the start of the Paleozoic Era, and the emergence of exclusively marine life. The most famous fossil site from the Cambrian period is found in British Columbia, Canada, known as the Burgess Shale, discovered in 1909 by paleontologist Charles Doolittle Walcott. This site has yielded exceptionally well-preserved remains of a rich invertebrate fauna that lived in the mid-Cambrian period 520 million years ago. If you had dived in the Cambrian in search of macroscopic fauna, you would have encountered a Lucigenia, a strange fossil that caught the attention of British paleontologist Simon Conway Morris in 1977. It was extremely thin, measuring only 2 centimeters in length, with a soft trunk bristling with spines and supported on 10 pairs of high legs, as if walking on stilts. The 7 pairs of rear legs, equipped with claws, were likely used for advancement, while the 3 pairs of front legs, longer and thinner, seemed covered in a type of feathers. These were either sensory organs or served to capture suspended food particles in the water and bring them to the mouth, surrounded by teeth. The latter hypothesis seems plausible because the opening in the head is lined with teeth, and further back, there is a set of needle-shaped teeth in the throat. It is assumed, therefore, that food was chewed once and swallowed a second time in the throat. Thanks to the latest advances in electron microscopy, the fossil of a Lucigenia also reveals a pair of dark spots on its head, which could correspond to eyes. Thanks to these scientific advances, a more precise description of a Lucigenia related it to the onychophorans, a group represented by the Peripodous, vermiform animals living in tropical forests and relatives of the arthropods, which include crustaceans and insects. Another unusual animal from the arthropod group that intrigues scientists is Wawaxia. The first fossilized specimens were found in the Burgess Shale, but others have been recorded in China, Russia, Australia, and the Czech Republic. Its buoyed body, 5 centimeters in length, was covered by 8 rows of overlapping plates called sclerites. The sclerites acted as a shell to escape predator attacks and were topped by 2 rows of spines up to 5 centimeters high. Additionally, the scales of this natural armor, loaded with microscopic structures, reflected light like the back of a beetle. This was enough to dazzle and dissuade attackers from approaching. Wawaxia was at least inhospitable, as the examination of the fossils shows that on its back lived shells similar to those of clams. Therefore, it is assumed that it simply rested on the seabed and never burrowed. Its food consisted of bacteria found at the ocean floor. Truth be told, specialists have difficulty agreeing on Wawaxia's place in the tree of life. Some point to its close relatives among modern marine worms. Others suggest that since its oral organ resembles that of a snail, it is its ancestor. There are also those who believe it is neither a worm nor a mollusk, but a representative of a distinct group that has already disappeared among the arthropods. Cambrian period, a pivotal era in Earth's history, was marked by the Cambrian explosion, a phenomenon that saw a rapid diversification of life forms approximately 541 million years ago. This era laid down the foundation for modern marine ecosystems and introduced a variety of organisms that demonstrated significant evolutionary advancements, including the development of hard body parts like shells and exoskeletons, which not only offered protection from predators, but also provided paleontologists with fossil evidence that helps us understand the early history of life on Earth. One of the most fascinating aspects of the Cambrian period is the emergence of complex food webs. Unlike the simpler ecosystems of the Ediacaran period, the Cambrian seas teemed with predators and prey, leading to an arms race between species. This period saw the development of eyes and other sensory organs, enabling animals to better detect their surroundings and evade predators, or find prey more effectively. Anomalocaris, often heralded as the first superpredator, is a prime example of Cambrian innovation. Reaching up to 1 meter in length, Anomalocaris had a pair of large, grasping appendages in front of its mouth, which it used to capture prey. Its body was segmented with lobed fins that provided agility and speed, and its compound eyes offered sharp vision, making it a formidable hunter of the Cambrian seas. Another noteworthy creature from this time is Hallucigenia, which puzzled scientists for decades due to its bizarre appearance. Initially, researchers had difficulty understanding its orientation. Its spines were mistaken for legs, and its legs were thought to be tentacles. Hallucigenia had a series of spines along its back and a set of slender, leg-like appendages that it used for walking. This creature is an early example of a velvet worm, showing the diversity of life forms that were exploring new ecological niches. The Cambrian period also saw the rise of the first true arthropods, a group that would eventually include insects, arachnids, and crustaceans. Trilobites are among the best-known Cambrian creatures, with their hard exoskeletons, segmented bodies, and compound eyes. They were highly successful, adapting to a wide range of marine environments, from shallow waters to the deep sea. Burgess Shale and the Chungjiang fossil sites are among the most significant Cambrian localities, providing a window into the diverse and complex ecosystems of the time. These sites have revealed a wide array of organisms, many of which defy easy classification into modern animal groups, showcasing the experimental nature of Cambrian evolution. The Cambrian explosion represents a critical point in the history of life on Earth, marking the moment when the biosphere dramatically diversified. The evolutionary innovations of this period laid the groundwork for the complexity of life we see today. Understanding these ancient ecosystems not only sheds light on the origins of modern biodiversity, but also on the evolutionary processes that drive the emergence of new species and the complex interplay between organisms and their environments. Throughout these geological eras, the long-standing star has been the trilobite. These creatures were ubiquitous in the Cambrian seas, inhabiting every imaginable habitat from coral reefs to the ocean floor for over 270 million years. To date, more than 20,000 species have been documented. Trilobites varied greatly in shape and size, ranging from as small as a fingernail to as large as 70 centimeters, though most species measured between 3 and 10 centimeters. Their bodies were segmented into 3 parts both longitudinally and laterally, consisting of a head with 3 lobes, hence their name, a thorax and a tail. The head featured a central part flanked by 2 cheek-like sections that housed eyes composed of hundreds of facets, similar to those of a dragonfly. Each body segment was equipped with 2 appendages, which could be antennas, mouthparts, or legs, varying significantly from one species to another. Some species bore spines that extended and twisted into peculiar shapes, while others had eyes on stalks protruding from their bodies. Most trilobites scavenged the ocean floor for food, and their morphology provided them with a significant advantage in their aquatic environment. Their diets were diverse, including predators, scavengers, slime eaters, or filter feeders. Trilobites are believed to be closely related to spiders and scorpions. The marella, affectionately dubbed the lace crab by paleontologist Charles D. Walcott, who discovered it in the Burgess Shale, thrived in Cambrian waters, with over 25,000 specimens found. Measuring up to 2.5 centimeters, it had two long extensions atop its head that curved backward, giving it a horseshoe appearance. Below, two pairs of thin antennas likely helped it navigate the sandy seabed, while another pair of robust, hairy appendages at the bottom of the head could have aided in propulsion. The rest of its body consisted of 17 to 26 segments. The feeding habits of marella have sparked various theories, suggesting it might have been a hunter and scavenger, or it might have filtered water through its many leg-like appendages equipped with thread-like protrusions. Our exploration of Cambrian marine creatures continues with the cephalopod Nectocheiropteryx. Little is known about this creature, but fossils from the Burgess Shale provide invaluable insight into its anatomy and lifestyle. Its cylindrical, soft, flattened body, measuring between 2 and 5 centimeters in length, featured two dorsolateral fins resembling a mix between a ray and a squid, enabling it to swim swiftly and agilely. It also had two long tentacles extending from its rigid head. Nectocheiropteryx is intriguing because it possessed a pair of rod-shaped eyes at the base of its mouth and a flexible cone leading to an internal cavity with a pair of gills. This structure resembles the siphon, a tubular organ used by modern cephalopods for backward swimming, suggesting Nectocheiropteryx used it for propulsion. It likely fed on small organisms like plankton and bacteria, living in shallow waters near the coast. These anatomical features support the hypothesis that Nectocheiropteryx is an ancestor of octopuses and squids. Opabinia, one of the Cambrian's most peculiar animals, had a strange anatomy with a soft, segmented body 7 centimeters long, resembling a shrimp. It had 5 eyes on small stalks, 2 in front and 3 behind, and a flexible proboscis ending in a sort of claw, likely used for feeding. Lacking powerful jaws, it had to feed on soft food, extracting worms from the sediment. Opabinia had no legs. The 15 body segments were edged with articulated lobes possibly used for crawling and swimming. The fan-shaped tail fin is reminiscent of a lobster, aiding in movement and navigation. Initially considered a unique specimen, detailed comparisons with numerous living and fossil species have led researchers to relate it to other soft-bodied segmented animals, even remotely to arthropods. The Cambrian period was a pivotal moment for aquatic animal diversity, acting as a springboard for the explosion seen during the Ordovician period. This era, spanning 65 million years and starting 500 million years ago, was marked by significant continental fragmentation in the Paleozoic Era, the beginning of the closure of the Iapetus Ocean, bringing Laurentia and Baltica closer, and the Caledonian orogeny, which formed ancient massifs in Europe and North America, including the Appalachians. The opening of the Reich Ocean separated Avalonia, named after the mythical island of Avalon where King Arthur's sword Excalibur was forged, from Gondwana. Avalonia included England, Wales, southeastern Ireland, northern France, Nova Scotia, and New England. The Turquoise Sea separated Baltica from Avalonia. This period witnessed another burst of animal diversity, with an increasing number of deep-sea species, planktonic animals swimming in the open sea, and well-equipped predators. Constructed by sponges and other creatures, reefs grew and multiplied, providing shelter for more animals. At the same time, some ventured onto land in short excursions out of the water, leaving their marks on the shore. The era's vegetation was primarily mosses and lichens. Much of the primitive fauna lived in shallow seas near the coast, but for any animal capable of swimming far enough into the sea, the open ocean offered vast territory, new food resources, and perhaps fewer predators. Among crustaceans and other arthropods, the nautiloid is a mollusk related to squids and octopuses. Fossils found in Ordovician rocks, 470 million years old, show they were present worldwide. These animals gradually adapted to deep-sea life, believed to have initially been plant eaters that moved up and down in the water by filling and emptying gas chambers in their shells, changing the chemical concentration of their body fluids. This process allowed the shell to fill with gas, increasing or decreasing buoyancy. Nautiloids became more mobile, moving by jetting water through a hole near their head, and hunting with tentacles that brought food to their hard beaks. Most had shells only about 10 centimeters long, but some were enormous, reaching up to 6 meters in length, dominating the aquatic food chain. Fossilized shells show that nautiloids likely preyed on each other, and traces of preserved color on some fossils suggest that some species practiced camouflage, with gray and brown stripes on the upper shell allowing them to blend in with dark waters. Imagine a giant tadpole, and you'll have a good idea of what the earliest vertebrates looked like. Among them, Sacabambaspes junieri is one of the oldest and best known. It is considered a pioneer of fully skeletonized animals, with a maximum length of 25 centimeters. Its head, equipped with bony shields on the top and bottom, likely protected it from predators, especially large invertebrates. The rest of the body was covered with long scales. Lacking jaws, it had to suck up food from the bottom of the water and then crush it in its throat. The eyes were situated between two small nostrils, and the mouth was equipped with very fine plates. Sacabambaspes lived in shallow waters near the shore. Some fossils have scratches on the belly made while scraping the ocean floor. Today, the largest animals in the sea are vertebrates, such as whales and sharks, although some deep-sea squids closely compete with them. However, hundreds of millions of years ago, huge specimens dominated the seas, including the Pterygotus anglicus, named winged fish by Swiss naturalist Louis Agassiz, who first described it in 1839. He thought he was encountering a large fish. In reality, he stumbled upon an extinct group of arthropods, also known as sea scorpions. These creatures had bodies that could stretch up to 1.8 meters in length and were closely related to the group called Eurypteridae. It's demonstrated that they were adept swimmers. The species Pterygotus moved with 4 pairs of legs, while a 5th pair functioned more like fins. It was equipped with 2 forelimbs ending in powerful claws, ideal for seizing and killing prey. Its vision must have been exceptional, given its gigantic lateral eyes, complemented by a smaller pair positioned at the center of its head. Its body was streamlined for swimming, and its flat tail likely served as a fin for propulsion. Despite its formidable size and appearance, the Eurypteridae, aquatic ancestors of the millipedes, were arthropods with an external skeleton, a pointed tail, and a segmented body sporting up to 28 pairs of legs. Comparable in size to a large shrimp, about 10 centimeters, they resembled a cross between a lobster and a woodlouse. The oldest known fossils of these creatures, dating back to the late Cambrian period, suggest they were among the first animals to venture onto land, where shores teemed with microbes and bacteria, a veritable feast if they could reach it at low tide. Venturing out of water also offered an escape from predator attacks. The late Ordovician period witnessed a major extinction event, wiping out 85% of existing species and affecting both benthic organisms, like trilobites, echinoderms, and graptolites, and pelagic forms, such as nautiloids. This mass extinction has been linked to glaciation occurring at the time, with the South Pole located in present-day Niger, and much of Gondwana covered by an ice sheet twice the size of modern Antarctica's. This led to a 50-meter drop in sea levels, drying up shallow seas that had been teeming with life. In addition, an anoxic event, extreme drops in oxygen levels in the sea, destabilized marine ecosystems. What was once a vibrant ocean became a desolate one. This crisis lasted between 1 and 2 million years, giving way to the Silurian period around 435 million years ago. At the start of this third Paleozoic era, which began 444 million years ago and lasted over 28 million years, the melting of polar ice caps caused a rise in sea levels and the flooding of continental shelves. Following the closure of the Iapetus Ocean, the landmass Avalonia joined with Laurentia and Baltica, forming the Old Red Sandstone continent, now known variably as Euramerica or La Russia. The massive continent of Gondwana was separated from this landmass by the Reich Ocean and the Paleotethys Sea. The Silurian marked the dawn of the Age of Fishes, with the emergence of jawless vertebrates, known as ostracoderms, and their bony external armor. However, jawed vertebrates, or gnathostomes, also appeared, leading to the terrestrialization of invertebrates, including annelids, arthropods, and gastropods. The oldest macrofossil plants date back to the Silurian but are scarce. Following the mass extinctions at the end of the Ordovician, life once again flourished and diversified. Coral reefs were numerous in the island arcs bordering the Panthalassa and Paleotethys, as well as in the shallow seafloors, with a generally warm climate allowing their spread far beyond the intertropical zone. Corals were primarily of the tetrachlorala, also known as rugose and tabulate corals. The emblematic animals of the Silurian were the eurypterids, already present in the Ordovician. Their story continued, never verified as much in form and size. The most significant event among vertebrates was the appearance of jaws, which formed from the second gill arch of the agnathans. The first jawed vertebrates, or gnathostomes, were the acanthodians, with their spiny fins, and placoderms, whose front body was encased in a bony shell. Placoderms were the first vertebrates with jaws and movable teeth, appearing in the lower Silurian. They also introduced an even number of fins, which later evolved into the limbs of terrestrial vertebrates. Specimens of a species dating back 380 million years, found in the Gogo Formation, a fossil site in Western Australia, contained fossilized embryos. Thus, the placoderm is one of the earliest known vertebrates to have produced fully developed live young instead of laying eggs. However, the most striking and peculiar feature of placoderms is the bony plates covering their head and upper body. This armor suggests that the Silurian seas were a merciless environment where fish preyed upon each other, not to mention the threat from invertebrate predators like nautiloids and sea scorpions. Placoderms awaited their prey by lurking on the seabed or hunting in open waters. Dunkleosteus stands out as the largest placoderm, reaching lengths of up to 6 meters, with jaws capable of exerting a force of 500 kilograms. Other specimens, however, fed on marine plants. For example, Titanichthes, one of the most impressive with its 8-meter length and 1-ton weight, lacked teeth and likely filtered plankton suspended in the water, similar to the modern whale shark. However, giant placoderms were rare, and most measured between 30 centimeters and 1 meter. Placoderms were found worldwide, living in both fresh and salt water. When they went extinct at the end of the Devonian period, they left the oceans to two groups: bony fish, which include most modern fish and the ancestors of terrestrial vertebrates, and the cartilaginous fish, like sharks and rays. According to fossils of acanthodians, this group of jawed vertebrates appeared about 400 million years ago. Acanthodians are characterized by having long bony spines at the front of their pectoral fins, as well as on their dorsal and anal fins. Their bodies were covered in small, square scales. Like sharks, they had a heterocercal tail, meaning it had two unequal lobes. Some acanthodians were predators that used their large eyes to spot prey, while others lacked teeth and were content to filter water. These predators thrived worldwide, colonizing seas and rivers until they went extinct in the Permian, about 250 million years before our era. The invasion of the continents continued with the appearance of the first terrestrial arthropods and larger plants, such as Cooksonia. Terrestrial life was confined to a narrow strip of wetlands around rivers and lakes. The best candidates for the title of pioneer terrestrial animals are the ancestors of today's millipedes and centipedes, the group Myriapida. Numum was a relatively small creature, measuring just over 2 centimeters long. However, its most striking feature was its large number of legs, up to 40 pairs. The holes running along its body allowed it to breathe, providing oxygen to its cells. They also show that the animal lived on land. Paleophanes is one of the oldest known scorpions, though its exact size is unknown. It probably measured no more than 8 centimeters. This small size may have been an adaptation to the scarcity of available food at the time. Its body was flat, and its long tail had a sting at the end. The most striking feature of Paleophanes is its large claws, which may have been used for capturing prey and defense, and could have posed a serious threat to smaller prey. As for vegetation, a type of primitive plant appeared, Cooksonia. The size of Cooksonia varied from a few centimeters to 1 meter in height. Microscopic analysis reveals a functional vascular system, allowing it to transport water and nutrients from the soil through the stem, thus ensuring a constant water supply. Therefore, Cooksonia could easily adapt to periods of heat and drought and survive them. Stomata have also been found in Cooksonia fossils. These are small holes in the cuticle wall that allow gas exchange with the cells. Therefore, they are its respiratory system, without which it could not have developed. Without roots, leaves, or flowers, it consists of thin, branched stems. The stems end in a trumpet-shaped structure called a sporangium, which serves to disperse spores outside the plant to colonize the surroundings. These small plants dominated the continents for 40 million years and were an important step in the evolution of terrestrial plants. Among their descendants are some of today's best-known plants, such as ferns, mosses, and flowering plants. Additionally, by diffusing oxygen into the atmosphere and stabilizing soils, they also contributed to the arrival of terrestrial animals. The Devonian is situated between the Silurian and Carboniferous. This period extends from 418 to 359 million years ago. The Devonian period is marked by the disappearance of the Reich Ocean, allowing the supercontinent Gondwana to begin its slow drift towards Laurussia. This period saw the transition from fish to tetrapods, animals with 4 limbs and a neck, as well as the appearance of hexapods, which group insects and arthropods with 3 pairs of legs. Apart from the Panthalassa, most of the Paleozoic's Paleogene was closed during the Devonian, leading to a paleogeographic configuration. Forests were established in the equatorial regions of Laurussia, participating in photosynthetic activity that allowed the development of the ozone layer. All these events took place in a generally warm climate, responsible for the development of oxidized siliciclastic sediments, the old red sandstone, and carbonate rocks in which coral formations thrived. The uniformly warm climate of the early Devonian favored the development of reefs. The reef-building animals are invertebrates that live in colonies called stromatoporoids. Dunkleistus, for example, is a formidable predator and a threat to the giant eurypterids, although they were already present at this time. Sharks were not yet the supreme predators of the seas. They were joined by several representatives of the groups of scaly fish, namely the actinopterygians, acanthodians, and sarcopterygians. Graptolites, classified as algae, sponges, hydrozoans, bryozoans, and theropods, disappeared at the end of the Lower Devonian. Only one family of benthic graptolites passed into the Carboniferous. The seafloor remains dominated by brachiopods, of which only relics remain in our current seas. Mollusk bivalves became diversified and abundant shellfish in shallow coastal waters, as is still the case today. Large nautiloid mollusks began to decline but gave rise to the omnipresent ammonites in the Mesozoic seas. Echinoderms, mainly crinoids or sea lilies, form true sea grass beds locally. Devonian fish can be divided into 2 main groups: agnathans, jawless fish, and gnathostomes, or jawed fish. Of these 2 groups, agnathans were the ones that had the most difficulty surviving the great biological crisis at the end of the Devonian. Of the 6 known groups at this time, 4 went extinct. Of those that survived, today only a few species remain, such as lampreys and hagfish. Among the gnathostomes, destinies were diverse. On the one hand, the last ostracoderms disappeared after the Devonian, as did the last placoderms. On the other hand, sharks and rays have thrived to this day. In the Devonian, several subgroups of sarcopterygians appeared, and one of them was the origin of the first tetrapods, a notable evolutionary success. With 29,000 current species, not counting all those that have gone extinct, today only a dozen species of fish, along with coelacanth and lungfish, belong to the sarcopterygians. Actinopterygians, ray-finned fish, are an undeniable evolutionary success. With about 29,000 species currently roaming the waters of the world, they are the largest group of vertebrates. The Eusthenopteron was one of the sarcopterygians that could conquer the land. It had a pair of pelvic fins and a pair of fleshy pectoral fins, each connected to the body by a single bone. These bones are analogous to the bony limbs of terrestrial tetrapods, amphibians, reptiles, birds, and mammals. In these fish with fleshy fins, the swim bladder is modified to allow air breathing. The bony limbs were used for swimming in water, but also for crawling along the shore. Everything indicates that the Eusthenopteron could have reached 1.8 m in length. However, most paleontologists agree that it never left the water. Tiktaalik, thanks to certain aspects of its anatomy, seems to be close to terrestrial animals. It was discovered on Ellesmere Island in the Canadian Arctic archipelago. It measures up to 2.5 m and has a flattened head that can rotate thanks to a mobile neck. The holes that could be assimilated to nostrils probably allowed it to breathe on land. Its fins, equipped with strong bones and a wrist-like joint, could have helped it rise. Thus equipped, it could probably move in shallow waters, but also travel short distances along the coast, much like a crocodile. It must have prowled rivers and swamps, using its powerful fins and mobile neck to hunt other fish, which it tore apart with its sharp teeth. It is assumed that Tiktaalik did not spend much time out of the water, based on the impressions left in the rocks where its fossils were found. The transition from fish to tetrapods is one of the key events in the history of terrestrial life, leading to the colonization of the land surface by vertebrates. However, for this change to occur, two major problems had to be solved. Towards the end of the Frost period, the world experienced a significant shortage of oxygen, an event that came to be known as the Kellwasser phenomenon. This occurred when molten lava made contact with seawater, releasing toxic substances such as metals including silver, gold, chromium, iron, magnesium, and others. The oceans became polluted, leading to devastating effects on marine life. The release of gases into the atmosphere resulted in massive emissions of carbon dioxide, gradually enriching the air with greenhouse gases. Consequently, temperatures began to rise, and ocean currents altered, with water temperatures exceeding 30 degrees Celsius at the equator, leading to a dire situation where aquatic life was severely threatened. 250,000 years after the initial eruption, Earth continued to discharge magma, and with the atmosphere already saturated with carbon dioxide, vegetation flourished, covering the planet's surface. Over millennia, fallen leaves accumulated on the ground, forming the first layer of a global musk. This nutrient-rich soil was washed into the seas by rain, where it was absorbed by algae that grew uncontrollably, consuming all the oxygen and suffocating aquatic life. Coastal areas became overrun and choked with plant life. Until now, such eruptions had occurred at sea, but they began to take place on land, polluting the air with sulfur dioxide, methane, and carbon dioxide, leading to massive eruptions and the release of vast ash clouds several kilometers high into the atmosphere. Earth was in turmoil, its skies darkened by ash, and wildfires erupted globally. The sun was blocked out, leading to a volcanic winter where temperatures dropped by around 20 degrees Celsius, and the plankton, a crucial part of the food chain, vanished. Fish eggs were decimated in a widespread massacre. Salvation came through oxygen-producing trees, which eventually stabilized temperatures, heralding the return of the seasons and a resurgence of diversified life. This extinction event wiped out between 50 and 70% of species. In the early Carboniferous period, the continents Laurussia and Gondwana reformed into a single landmass, known as the Small Pangaea, surrounded by the superocean Panthalassa. Tectonic movements raised sea levels, drowning a vast number of plants in the seas, even as spiny fish began to appear more frequently, though echinoderms and crinoids dominated the ocean floors, thriving in the immense, lush swamps alongside arthropods. The era also saw the evolution of tetrapods and amphibians during the Devonian period, as well as the first reptiles on land. Devonian ferns gradually gave way to seed-bearing trees, which, during fires or floods, were buried and decomposed, thereby preserved beneath growing organic matter. This plant material, deeply buried and heated over millions of years, transformed into coal through a process known as carbonization. Around 330 million years ago, conditions were so conducive to the formation of coal that the era was named the Carboniferous period. The rulers of the Carboniferous jungles were a group of vascular plants, the most common of which was called lepidodendron. This majestic plant could climb up to 30 meters in height, with a trunk diameter of 1 meter. Its initial growth was rapid and unbranched until the single, enormous shoot reached the canopy, where the tree branched out into a beautiful crown whose tips bore cones containing spores. Another terrestrial plant of the Carboniferous period, Glossopteris, was found in rocks across South America, Southern Africa, Madagascar, India, and Australia. Despite being a major component of coal, little is known about it. It was a woody plant with a trunk diameter of 80 centimeters, suggesting it could also have reached up to 30 meters in height. The Carboniferous was a time of giant insects, with dragonflies the size of large birds, cockroaches as big as mice, and scorpions over 50 centimeters long. However, the gold medal goes to Arthropleura, the largest invertebrate of its time. Although no complete fossils have been found, scientists agree that based on the study of fragments and fossilized tracks, it could have been up to 2 meters long and 50 centimeters wide. This relative of modern millipedes was covered in a thick, heavy shell made of chitin, a hard substance found in the exoskeletons of living insects, and lived in tropical swamps covered by forests of tree ferns and other primitive plants. Since no fossilized mouths have been discovered, scientists assume it was a herbivore, as fossil feces attributed to Arthropleura contain plant spores. Ballerpetten woody was discovered in the famous Scottish site of East Kirkton within hollow fossilized tree trunks. It is conceivable that these small amphibians sought refuge there from fatal landslides. The morphology of Ballerpetten is unusual, with its rounded skull and elongated body about 20 centimeters long, resembling a salamander. Its well-ossified and robust wrists and ankles suggest terrestrial locomotion. It had a large tympanic opening in the back of the skull, forming a rounded window useful for detecting environmental sounds, making it one of the few fossil amphibians with about 40 teeth in the upper jaw, while the lower jaw had only about 20, indicating a carnivorous or even insectivorous diet. As for reptiles and lizards, Hylonomus is the oldest known specimen. The first discovery of Hylonomus fossils occurred over 150 years ago on the Canadian island of Nova Scotia, which during the Carboniferous period was located in the tropics. These were buried within a hollow and fossilized tree trunk, indicating that Hylonomus had evolved sufficiently to spend its life on land, roaming forests in search of insects and millipedes. Its body was approximately 25 centimeters long, including the tail. Hylonomus reveals the dawn of reptiles, and with them the appearance of the amniotic egg, allowing vertebrates to colonize land, with reptiles dominating for over 200 million years. Animal life in the Carboniferous also featured the development of giant insects, with Meganeura standing out as the ambassador of giant dragonflies. With a body length of 30 centimeters and a wingspan of 70 centimeters, it could be compared to a modern pigeon, flying over rivers and lakes, feeding on small insects detected by its sharp eyesight. The reason for the enormous size of Carboniferous period animals remains a topic of debate, but the most common explanation lies in the air's oxygen content. Today, it stands at 21%, but during the Carboniferous period, it reached 35%. This abundant supply of oxygen, stemming from the lush vegetation of the forests, promoted growth, benefiting insects, amphibians, and other invertebrates. Solitary or colonial corals built significant reefs in the warm waters of the Paleotethys, while brachiopods, echinoderms, and mollusks also thrived. Among the latter group, goniatites hold great stratigraphic interest. While some stegocephalans ventured onto land, others evolved in aquatic environments. This includes Curioscoti, a giant tadpole-like fossil discovered in ancient mines near Edinburgh, measuring up to 2 meters long. With its large skull and atrophied limbs, Curioscoti lived in shallow freshwater environments, resembling a snake. Its poorly ossified pelvis and spine allowed for some flexibility, and it was carnivorous with a preference for fish, possessing several fangs within its mouth, even on the palate. Its cranial kinematics, comparable to that of snakes, indicate it could open its jaws wide, swallowing prey much larger than itself. Another Carboniferous period stegocephalian, Spatialemurus, had a modestly sized skull, about 20 centimeters long and flattened like a frisbee. Its skull featured peculiar bean-shaped eye sockets that were closely set, possibly housing eyeballs, glands, or electroreceptive organs for detecting prey. Spatialemurus's dentition included many small, fine teeth but lacked fangs, with only the lower jawbone bearing about 120 teeth. The Carboniferous period, spanning from about 359 to 299 million years ago, marks a fascinating chapter in Earth's history, characterized by its significant geological, atmospheric, and biological developments. During this era, the Earth's climate was warm and humid, which, coupled with high oxygen levels, created ideal conditions for the lush growth of extensive forests. These forests were dominated by large ferns, horsetails, and the towering lepidodendrons and sigillarias, which could grow over 100 feet tall. The abundant plant life not only shaped the landscape but also played a crucial role in the formation of extensive coal deposits, which is why the period is named Carboniferous, meaning coal-bearing. The high levels of oxygen during this period, which at times reached as much as 35% compared to today's 21%, are believed to have contributed to the gigantism observed in many insects and arthropods. Creatures such as the dragonfly Meganura could grow to wingspans of nearly 2.5 feet, making them some of the largest known flying insect species. This gigantism is attributed to the increased oxygen's ability to diffuse more efficiently into organisms' bodies, allowing for larger sizes. However, this golden age for giant insects and lush forests came with its challenges. The Carboniferous period was also a time of significant tectonic activity, leading to the formation of the supercontinent Pangaea. This tectonic movement influenced global climates, ocean circulation, and sea levels, contributing to the formation of extensive ice sheets towards the end of the period, particularly in the southern hemisphere. This transition marks the boundary between the Carboniferous and the following Permian period, characterized by drier climates and the decline of many dominant Carboniferous species. The rich biodiversity of the Carboniferous period did not limit itself to flora and giant insects. The period also saw significant evolutionary advancements among vertebrates, particularly the development of the amniotic egg, which allowed for the further colonization of terrestrial environments by vertebrates. This period witnessed the diversification of early amphibians and the rise of the first reptiles, marking a pivotal point in vertebrate evolution. The amniotic egg shell provided protection and nourishment to the developing embryo, enabling it to develop on land rather than in water, a major evolutionary advantage that allowed these creatures to explore new ecological niches. The end of the Carboniferous period and the transition to the Permian were marked by significant environmental and climatic shifts. The formation of Pangaea disrupted ocean currents and led to a drier climate over much of the supercontinent, reducing the extensive swampy forests that had characterized the Carboniferous landscape. This environmental change led to the decline of many species adapted to the dense, wet environments, while others that could adapt to the new conditions thrived, setting the stage for the next chapter in Earth's evolutionary story. The legacy of the Carboniferous period is still evident today, not only in the vast coal deposits that have been a crucial energy source for humanity, but also in the evolutionary innovations that shaped the future of life on Earth. The period's unique conditions fostered a remarkable chapter in the story of life, leaving a lasting impact on the planet's geological and biological history. The tips of their teeth were equipped with small valves, suggesting they ingested large volumes of water or mud to filter out tiny invertebrates or fish. This feeding mechanism likely played a crucial role during the late Carboniferous period, a time when the planet experienced a cooling phase. Despite relatively mild temperatures on the continent of Eurasia, the southern regions, including the continent of Gondwana, were not as fortunate. In fact, Gondwana was partially enveloped in ice, a condition that persisted for approximately 80 million years until the dawn of the Permian Era, which commenced around 295 million years ago and spanned about 50 million years. This era significantly marked the end of the Paleozoic Era. A pivotal geological event during this time was the collision of the landmasses of Siberia and Kazakhstan with Gondwana, leading to the formation of Pangaea approximately 450 million years after the disintegration of Rodinia. Despite this unification, several continental fragments remained, including northern and southern China. This continental drift induced climatic shifts, transforming the lush, swampy landscapes of the Carboniferous into arid deserts and mountain ranges formed from the collision of continental plates. The global sea level continued to decline, reaching levels similar to today's oceans. East of Pangaea lay the Tethys Ocean, while to its west sprawled the vast Panthalassa Ocean, positioning Pangaea almost from pole to pole, subject to extreme and variable climatic conditions with temperatures ranging from 0 to 40 degrees Celsius in a single day. The South Pole remained frozen since the glaciation at the end of the Carboniferous period, whereas the rest of the continent experienced a predominantly dry and arid climate. This reunification of landmasses resulted in a relatively uniform terrestrial fauna, with reptiles emerging as the dominant vertebrates, gradually replacing amphibians. Among these, the rise of the amniotes was notable. However, despite their current small size, amphibians' ancestors, such as the Archaeops, did not go unnoticed. Their fossils, discovered in the lower Permian rocks of Texas and New Mexico, represent the Temnospondyli group. These creatures had large, flat skulls with mouths full of sharp teeth, likely splitting their time between marshlands and dry land, feeding on small fish and terrestrial animals. Yet, a formidable predator existed among them, the Dimetrodon. Although it may resemble a dinosaur, Dimetrodon was not their ancestor but belonged to the synapsid group, predating dinosaurs. It stood atop the food chain as one of the oldest superpredators, with species varying in size from 60 centimeters to nearly 5 meters, and the most robust specimens could weigh up to 300 kilograms, surpassing the weight of an adult brown bear. Its jaws housed formidable serrated and sharp canine teeth at the front, making its bite incredibly effective for killing, dismembering, and consuming large amphibians and fish. It had a powerful tail, muscular and sturdy legs, and a back adorned with long, sail-like spines supported by the vertebrae. The function of this dorsal sail has long puzzled scientists, with some paleontologists suggesting it might have served for camouflage among tall reeds, spinal support, or body temperature regulation. Others believe the sail was a colorful ornament to attract mates or intimidate rivals, with the truth potentially being a combination of these theories. The Permian period ended with a catastrophic crisis around 252 million years ago, marking the most significant ecological disaster in Earth's history. This event saw a drastic reduction in marine life, with 96% of species perishing. Reef formations and other bottom-dwelling creatures faced similar fates, with brachiopods, bryozoans, and especially crinoids losing diversity. Scientific estimates suggest that up to 75% of terrestrial animal and plant species went extinct, including almost all reptiles. The causes of this extinction event remain a subject of debate, with hypothesized factors including ocean anoxia, massive volcanism in Siberia, a significant drop in sea level, or a combination thereof, although the volcanic hypothesis prevails. The extensive lava flows covering 2 million square kilometers significantly altered Earth's climate, rendering many areas uninhabitable. Plants were among the first to be affected, with studies of fossilized pollen, rocks, and sediments in Australia revealing high nickel levels from Siberian volcanic eruptions that spread through the atmosphere and gradually poisoned plant life. This led to a domino effect on the food chain, affecting herbivores and carnivores alike. Nickel contamination also impacted the oceans, already suffering from global warming. Moreover, as Earth's temperature rose to 50 degrees Celsius, methane from the oceans evaporated, exacerbating the greenhouse effect and further reducing atmospheric oxygen levels. This Permian-Triassic crisis marked the end of the Paleozoic and the beginning of the Mesozoic Era. However, several species managed to survive this mass extinction, termed the disaster fauna, including Lystrosaurus, a mammal-like reptile resembling a cross between a dog and a boar, which became a distant ancestor of modern mammals and spread across Pangaea as life continued to evolve. Soon after, new species emerged, with dinosaurs dominating the Earth throughout the Mesozoic period. The Mesozoic Era, commonly referred to as the Age of Reptiles, represents a momentous chapter in the Earth's chronicle, stretching for an impressive span of approximately 180 million years. This captivating era commenced with the inception of the Triassic period and concluded with the cessation of the Cretaceous period. It is intricately divided into 3 distinct periods: the Triassic, Jurassic, and Cretaceous. The Triassic period, commencing approximately 252 million years ago, witnessed a gradual resurgence of the Earth's delicate ecosystems following the catastrophic Permian-Triassic extinction event. Against the backdrop of a dynamic geological landscape, the continents embarked on a ceaseless drift, provoking the gradual fragmentation of the colossal supercontinent Pangaea. This process, in turn, facilitated the formation of nascent landmasses, ushering in an era of geographic transformation. The climate, during this epoch, leaned towards arid and torrid conditions, with vast stretches of deserts dominating the terrain. It was amidst this climatic tapestry that reptiles, spearheaded by the archosaurs, emerged as the dominant class of organisms, adroitly occupying the ecological void created by their extinct counterparts. The Triassic period also witnessed the advent of the first dinosaurs, sharing their dominion with other reptilian inhabitants such as crocodiles and turtles. The culmination of this period was marked by yet another mass extinction event, decimating numerous marine and terrestrial species, further altering the course of life's progression. The Jurassic period, commencing approximately 201 million years ago, resides in the annals of history as a time of unparalleled diversity and the emergence of iconic dinosaurs. As the relentless tectonic forces engendered the continued separation of landmasses, Pangaea underwent a transformative metamorphosis, giving rise to Laurasia in the north and Gondwana in the south. The climate, during this juncture, basked in a perpetual embrace of warmth and humidity, fostering the proliferation of exuberant forests teeming with a kaleidoscope of plant life. Against this verdant backdrop, dinosaurs thrived and diversified, venturing into various evolutionary pathways. The colossal sauropods, distinguished by their elongated necks, such as the majestic Brachiosaurus and Diplodocus, commanded attention, while the fearsome theropods, including the renowned Allosaurus and the mighty Tyrannosaurus rex, instilled awe and trepidation. The oceans, too, bore witness to a plethora of remarkable creatures, such as ichthyosaurs and plesiosaurs, while the skies were adorned by the graceful flight of pterosaurs, the winged reptiles. The Cretaceous period, commencing approximately 145 million years ago, serves as the culminating epoch of the Mesozoic Era. As the inexorable dance of continental drift unfolded, the final disintegration of Pangaea unfolded, shaping a world of increasingly diverse and disparate landmasses. The climate of this period was characterized by a prevailing warmth and elevated sea levels, which engendered the formation of expansive shallow seas and vibrant coral reefs. Dinosaurs continued their reign over the terrestrial realm, with novel groups such as the horned dinosaurs, ceratopsians, and the armored dinosaurs, ankylosaurs, making their appearance. The skies were graced by the awe-inspiring flight of pteranodons, the largest known flying creatures of that era. The Cretaceous period also witnessed the advent of flowering plants, which underwent a remarkable diversification and emerged as a vital source of sustenance for an array of organisms. However, the Mesozoic era met a precipitous end approximately 66 million years ago, precipitated by the catastrophic Cretaceous Paleogene extinction event. It is widely believed that the cataclysmic event was triggered by a colossal asteroid impact, which unleashed unparalleled devastation upon the Earth. This calamity resulted in the extinction of non-avian dinosaurs, alongside a myriad of plant and animal species. The aftermath of this cataclysmic event paved the way for the ascendancy of mammals and ultimately set the stage for the subsequent dominance of humans in the ensuing Cenozoic era. The Mesozoic era stands as an indelible testament to the profound transformative forces that have shaped our planet. It is a period marked by the ascendancy and supremacy of reptiles, the awe-inspiring evolution of dinosaurs, and the profound metamorphosis of Earth's landscapes and ecosystems. Its allure remains unwavering in the eyes of scientists, who are captivated by its mysteries, while its narrative continues to captivate the imaginations of people worldwide, serving as a testament to the indomitable spirit of life's journey across the vast expanse of time. Geologically, the Mesozoic era witnessed remarkable changes in the Earth's landscape and the configuration of its continents. At the onset of the era, the supercontinent Pangaea, which had formed during the late Paleozoic era, began to break apart. This process of continental fragmentation resulted in the formation of two major landmasses, Laurasia in the northern hemisphere and Gondwana in the southern hemisphere. The separation of these landmasses led to the creation of vast oceans and seas, which played a significant role in shaping the climate and influencing the distribution of life forms. Speaking of climate, the Mesozoic era experienced fluctuations in temperature and environmental conditions. During the Triassic period, the climate tended to be arid and hot, with vast desert regions dominating certain areas. However, as the era progressed into the Jurassic and Cretaceous periods, the climate became warmer and more humid, leading to the development of lush forests and abundant plant life. These diverse ecosystems provided a fertile ground for the evolution and diversification of various organisms. One of the most iconic groups of organisms that emerged during the Mesozoic era was the dinosaurs. These majestic creatures, classified as reptiles, dominated the terrestrial ecosystems for millions of years. Dinosaurs came in a wide array of shapes and sizes, ranging from the colossal long-necked sauropods to the fearsome carnivorous theropods and the armored herbivorous dinosaurs. Their evolutionary success and dominance during this era have captivated the imagination of scientists and the general public alike. While dinosaurs reigned over the land, the oceans were home to a rich diversity of marine life. Mesozoic seas teemed with fascinating creatures such as ichthyosaurs, which resembled modern-day dolphins, and plesiosaurs, known for their long necks and paddle-like limbs. These marine reptiles adapted to life in the ocean and occupied various ecological niches, showcasing remarkable diversity and adaptations. Another group of remarkable reptiles that thrived during the Mesozoic era were the pterosaurs. These winged creatures, often referred to as flying reptiles, possessed the ability to soar through the skies with their bat-like wings. Pterosaurs exhibited an astonishing array of sizes and shapes, from the small and agile Rhamphorhynchus to the gigantic and awe-inspiring Quetzalcoatlus. The presence of pterosaurs added an enchanting aerial dimension to the ecosystems of the Mesozoic era. The Mesozoic era stands as a testament to the dynamic nature of our planet and the incredible diversity of life that has evolved throughout its history. It is a fascinating chapter in Earth's chronicle, filled with captivating geological events, awe-inspiring creatures, and the remarkable story of evolution. Scientists continue to uncover new insights about this era, piecing together the puzzle of life's journey and deepening our understanding of the intricate interconnectedness of Earth's past and present. Thanks for your attention, and see you in the next video.